these are planes in three-dimensional space. So each one of these equations represents a plane. We talked about the number of solutions that a system of linear equations can have. How many solutions can a system have? So here's an example of two planes, possibly two of these equations, intersecting on a line. So the intersection of two planes is a line here. Perhaps there's a third plane that comes in somewhere, intersects the first two planes, somewhere here maybe. The whole line, which is the intersection of the first two, is intersected by the third plane. If a system has a unique solution, this is exactly the picture of the system of linear equations in the three-dimensional space. In fact, this hand-picked system of linear equations has exactly a solution just like that. Now, of course, it won't always be lucky to have a 3x3 system, which we can draw, visualize. Normally in application, systems are much, much larger, thousands and thousands of variables with thousands and thousands of constraints in those variables, represented by these hyperplanes, the rows. And would like to have a streamlined way of finding the solutions to the systems of linear equations. And one such method that we'll describe today is called the Gaussian method, Gaussian elimination. Many of you have seen this in high school or middle school, wherever that was. We'll review it and move on. If you haven't seen it, that's fine too. Okay, so let me tell you what the method consists of. This system of linear equations, let's work with this 3x3 system, will be written down in a matrix form, right? This is our shorthand way of writing down the system of linear equations. The reason we do this is because we just want to write less. We don't want to copy these variables x1, x2, x3 all the time. Just simply write this in a shorthand way. These coefficients on the left-hand side tell me what the coefficients in the equations are. And this is the right-hand side. We normally denote this as B. This system, okay, the generic form of the system, the general form of the system is AX equals B. So what is X here in this way of writing down the system of linear equations? What is X? So what is X, please?
X is the indices.
X is a vector?
Yeah, it's a vector, and it's a column vector. X1, X2, X3. That's X. When we say AX equals B, what is it exactly that we're writing down? We're looking, so we're looking for X1, X2, X3 that satisfy this vector equation that I'm writing down. So where does this come from? Why does it make sense, what I'm writing down? And if it doesn't make sense to you, why does it not make sense, and what doesn't make sense to you? So what exactly is it that I'm writing down, please?
You're multiplying the matrix of the coefficients by the vector of the variables, and the result is the is B, the vector B.
That is correct. So how do you geometrically, how do you imagine this? Okay, what is it? Is there that's absolutely correct. But is there a geometric way of describing what you've just said in our column space view of the system of linear equations? So these vectors here. So anyone, please help me out. These columns here are vectors in a three-dimensional space in R3. So these are vectors. They belong to R3, right? So these are vectors. They're somehow jutting out in all directions in the three-dimensional space. What are X1, X2, X3? That's a mixture of weights you can think of. How much do I have to stretch the first vector by? That's X1. How much do I have to stretch or shrink the second vector, second column vector by? That by shrinkage factor or expansion factor, extension factor is X2. How much do I have to multiply the third column vector of A by? That's the column vectors. These are the column vectors of A by. So that when I add them up, when I take this mixture, that is, this is called a linear combination of the column vectors of A. That's the terminology that goes with it. What linear combination of the column vectors of A give me the right-hand side B? B is this vector, the vector of the right-hand side. This is B. This is the B vector here. So what linear combination of the columns of A leads me to the vector B? That's the question that we're answering. And we take, as we mentioned last time, the geometric viewpoint. It's not some mechanical manipulation of numbers, although we'll talk about this mechanical manipulation now, and we'll keep in mind the geometric picture that corresponds to that algebraic manipulation of some numbers in a matrix, right? So again, this is the mixture of variables, x1, x2, x3, that we're looking for, that lead to this vector. So now let's carry out this procedure that we'll call Gaussian elimination, somewhat of a misnomer. Today it's called Gaussian elimination, but the first record that we have today of it comes from the Chinese mathematicians of the 3rd century BC, and that undoubtedly it was rediscovered many, many times throughout the ages, first in the Muslim world, and then perhaps not so much in Europe. In Europe, then it came about during Gauss. Well, Gauss has quite a few things named for him. He was one of the greatest mathematicians of all time. So if this name of this procedure changes, which it should, we don't know. Probably at some point it will change, but for now it's called the method of Gaussian elimination. All right, so here's what the method of Gaussian elimination looks like. We manipulate rows. So the Gaussian elimination is all about row manipulation. There are allowed operations on the rows of this matrix. This is called the augmented form of the system. Why an augmented form? Well, it's just a piece of terminology. You have this matrix, this original matrix A, and you have the right-hand side B. You just simply tack on the right-hand side to that matrix. Just write it like that. This line doesn't mean anything. It's just there to separate visually the right-hand side vector B from the matrix A. It doesn't serve any other purpose, just other than it's being a visual aid for you. There are 3 allowed row operations. Now, remind me from last time, before I list them all, what did we do last time when we talked about the row picture of the system of linear equations? What was the row picture all about? We talked about something, we said the row picture, and we sort of gave a solution of a 2-by-2 system last time. What was that about? Can somebody remember? We had a nice picture last time. We drew lines, and we did something to the system without changing the solution to the system. But recognizing the solution to that small system, 2-by-2 system, was very, very easy last time. Well, first of all, it was a small system. So each line, each equation in the system was a line, and we drew those lines. But then we did something to those equations, and we redrew the row picture of the system. Can anyone remind me what that was all about?
I don't remember exactly what it was, but I can tell you what the row operations are.
Okay. So, well, what do those row operations do? How do you imagine them geometrically? So when you so this is like, okay, yeah, please. What are they?
So you can do like you can interchange rows.
Okay.
And so like from a geometric perspective, that doesn't really
Yeah.
do much because it's literally just moving them around, shifting them around within the matrix itself.
Yeah, it's the same set of equations written in a different order, so that
Right,
clearly doesn't change the solution. Okay.
You can also multiply rows by constants, and
Okay.
so if you had I don't know, a line that would increase the slope of the line or
Oh.
just make it larger. I mean.
Okay, so let's see if that is correct. So here's one equation, x2. Let's stick with 2 of them, or maybe 3 of them, doesn't matter. 3 variables. That equals, I don't know, 17. Suppose now I multiply this by 2. Are you saying that this changes the slope of the line? Does this change the equation at all if you multiply so?
Oh wait, no, it's not changing it actually.
Yeah, it's still the same equation.
Thing.
It's the same equation. It's the 3-dimensional space, right?
Yeah.
So that doesn't change it. So apparently you can. So we're not rigorously proving these, although we could.
Yeah. So you can multiply them without effectively changing anything.
Okay.
And then you can also do row addition.
Okay. So what does that do to the system of equation? Maybe that adds some new solutions to it. Maybe that spoils everything for us. What if I add 2 rows? I'm looking. I need. So what we're after is we want to transform the system of linear equations in such a way that it's easy to recognize at the end of the day, after the transformations, it's easy to recognize the final solution. But of course, we should be transforming the system of linear equations in such a way that the solution to the final transformed version of the system is exactly the same as the set of solutions to the original system, because we are solving the original system of equations. If we do some operation that changes the solution set, that wouldn't be an allowed operation, right? So all the operations that we carry out must be somehow allowed operations.
I couldn't tell you exactly how it looks geometrically. I took linear algebra a while back, and I only remember like the algorithms for how to solve these things.
Okay, well, what does these things do? Where do these algorithms come from? Someone like you invented it, right?
Yeah.
So, so they imagined it, I'm pretty sure. Okay, so that was okay. So last time, I think we had a picture there of a 2x2 system, right? When we added a multiple of some row to another row, what it did is it pivoted one of the lines so that the intersection of the two lines didn't change. Do people remember that? It was a picture like that. Okay. So one way to remember things is to associate these processes with pictures, right? That's how it sticks in your imagination, right? This is how human beings normally, most human beings normally remember things, by having picture associations with the facts or processes or whatever, right? So does anyone remember that picture, or you know, that people forgot already what we did last time? So the point of what we tried to make last time is that adding a multiple of one row to another row does not change the solution set. And that, as you've just suggested, that's one of those allowed operations. Okay, so for example, here, my goal is going to be the following. I want to make these guys zeros, this -1 and 2, I want to make these guys zeros. So I'm going to rewrite the first equation that tells me that this is the first equation, and rewriting it without writing down x1, x2, x3 all the time. So that's the first equation. It just, this line that I've just written down, it tells me that x1 plus x2 plus x3 is 4. That's just a shorthand way of writing that down. How do I make a zero here?
-2 times row 1 plus row 2 replace row 2.
Okay, so that's exactly right. So here's what you're suggesting. You're suggesting that row 2 minus 2 times row 1, and write that down here. Okay, so let's do just that. If I subtract 2 times row 1 from row 2, I get exactly this. And you tell me if I'm wrong. -3. Okay, minus that's going to be 3, right? 11 minus 2 times 4. I end up with a 3 there. Okay. Now for now, I'm going to rewrite the last row. The last row is going to be -1, 0, 2, -3. Although when you practice with these things, you can deal with that row in the same step, but that wouldn't be good to do. What's the next step? Now I want to get a 0 in this position here. This -1 is bothering us. We want
row
0.
1.
Yes.
Row 1 plus row 3 replace row 3.
Okay. So row 1, row 3, I'm going to write it down first. This will turn out to be kind of important so that we don't mess up on the quizzes and so on. So we're taking row 3 and adding a multiple of a row that came before. That becomes kind of, it's not apparent why this should be the case now, but that's the way we'll proceed, because that's what the algorithm inside your computer that solves this does. It takes row 3, and in this case, it just simply adds 1 times row 2. So R3 plus R1 would be what the algorithm will perform, and it simply adds these up. So it doesn't do anything to the first row. It doesn't do anything to the third row. Okay, and it adds the first row to the third row so that we get this one, right? Okay, now the next step. Okay, now let me tell you one thing, looking ahead. This guy will be called a pivot. This guy's name will be a leading variable, if you want to call it. This leads this row. Leading variable, or pivot, is the name for this coefficient of x1. Okay, leaving that aside for a second. Now the next step is to make a 0 here. How do I do a 0 there?
You could do 1/3 of row 2 replace row 2.
We could do that. Sure.
And then add negative of that.
Yeah, we could do that. That's one way of doing it. Or I can just subtract. How about just simply subtract 1/3 of row? So notice that we have some free. So we have a few different ways. The matrix that we get after this process.
Well, the goal is to get ones on the main diagonal anyway. So just getting it down now would also work.
Okay. So in a moment, I will be asking you under what conditions. For those of you who know this process, please think about this now while I'm writing this down. The next step. Under what conditions will I not get those ones? So as you said, you want to get those. You want to get zeros here in this triangle. This will be called an upper triangular form of this matrix. I just exactly want to get a 0 here. So let's just do that. What I can do is I can subtract 1/3 of row 2 from row. In fact, let me just write it down here, what I'm doing. So that's one way. Or yes, you are also allowed to multiply the second row by 1/3, and then on the next step, add it or subtract it from row 3. Let's do it this way. Subtract row 3 minus 1/3 row 2. Okay, so let's write this down. It's going to be 1, 1, 1, 4. Okay, 0, 3 minus 3. Of course, I could be writing this down as like dividing this by 3. Yeah, like, okay, maybe that would be, but anyway, let's just do the way I've written it down. 0, 0, 3 minus 1/3 of R2. What is it going to be? 4, right? 1 minus 1/3 of 3. 0. Okay, now notice what I have. We're not done with the process of Gauss-Jordan elimination. But if you were asked to solve this system of equations, you already have a solution, right? By using back substitution, which is not what we'll be encouraging to do here. But if you're just algebraically solving this, you've got the solution. Well, let's write it down. What does this system say? Well, the first equation says that x1 plus x2 plus x3, okay, equals 4, right? The second says that x1 minus x3, I'm sorry, x2 minus x3 is 1. And the third says that 4 times x3 is 0. Okay, I rewrote this. Of course, the whole purpose of keeping it in a matrix is that I don't have to write this down. But let's write it down, just the first couple of times we're doing this. So underneath here, I'm going to have the system itself. Now I can do back substitution, right? So what, from the last equation, I can see that x3 has no way but to be a 0, right? There's no way for x3 to go but be a 0. Otherwise, the fourth equation would be violated. Okay, so notice that this is one of those planes where x3 is, what plane is this in the three-dimensional space?
Is that Z?
Yeah, Z equals 0. So this is the xy plane, right? I mean, x1, x2 plane. Okay, so now x3 is 0. What does x2 have to be? I plug in 0 here. X2 has no way but to be 1. You know, can't escape being 1. Well, now x2 is 1 and x3 is 0. What does x1 have to be? X1 has no way but to be a 3, right? So what's my solution? So I read off the solution by doing the back substitution here, by saying that my solution x, the vector x that I was looking for, is going to be 3, 1, 0. 3, 1, 0 is my vector x. Now, of course, if this row manipulation does the job as intended, okay, so what we're doing here in row manipulations, where we're shifting those hyperplanes into three-dimensional space. If you have time and would like to, think about this, you can imagine these planes shifting, but not necessary. It's much quicker to algebraically write this down. You certainly don't have time to exercise that imagination during the quiz and think of hyperplanes as unless you have an exceptionally vivid imagination. Some people do. It's much quicker to do this algebraically. Okay, so coming back to this view, to the column view of the system of linear equations. This is our solution. We were looking for x1, x2, x3 that make this happen, here. Is this true? Well, let's take a look. So 3 times that, 1 times the second vector, 0 times the third column vector. Is this equation satisfied? Yes. If you add those vectors, so apparently I had to stretch the first column vector 3 times. I had to collapse the entire vector column 3 of A, collapse it into a singularity. This is called the singularity of 0. Let's go with this later. Okay. Okay. Collapse it to 0. I'm taking no multiples of the third column. So I need 3 times the first column vector stretched, add to it the second column vector, and I'm led exactly to the solution, right? So if you add those vectors up, you'll get exactly this solution. So indeed, the solution that the row manipulation gave us and the back substitution is consistent with our column view of the solution set of the system. Now, the method that we described and the allowed row manipulations that one of you explained to us, what were they? Maybe somebody else can explain the three allowed row operations. Let me go quickly with this because we need to move on. So we have 3 allowed row manipulations, operations. Those are, you're allowed to exchange 2 rows at any time. Okay, the need to do this in this example didn't come up, but in the next examples, in the examples coming up, we'll see the need to do this. We are able to multiply a row by any constant. That doesn't change the solution set. That's number 2. Number 3, we can add a multiple of any row to any other row. That doesn't change the solution set. These are the 3 allowed row manipulations that allow us to bring the original matrix, the system of linear equations. This is a small example of a 3 by 3 to what's called, in this case, upper triangular form. This is called the row echelon form. In this case, an upper triangular form, also called the row echelon form. Now we'll do an example. Why echelon? What's that all about? We'll talk about that in a minute. Now let me ask you this. Okay, so apparently we had one solution here, that X. It's a unique solution to the system. There's no way the system has any other solution. This is the only solution the system has. This is, by the way, if I view A as a transformation that we mentioned last time, so A was a function, remember we talked about A is a linear function, applied to some X leads me to B, okay? This is a reversible operation. It will turn out later that this A, this matrix A that gives me that transformation that leads this vector X to this vector B is an invertible operation. This matrix will have an inverse because we found that this 3 by 3 matrix has a unique solution. The system of equations has a unique solution, and that A is invertible. More on that later. This is looking ahead. Now tell me what could have gone wrong. What could have gone wrong so that I wouldn't be able to find a unique solution? When can this, what could have happened so that this system, or perhaps I needed to change some entries there, wouldn't have a unique solution, right? So this particular case, these handpicked entries in this matrix correspond to the situation where the planes look exactly like that. We have a unique solution. Apparently this vector here, here's the origin of the 3-dimensional space. This vector is the 3, 1, 0 vector. This vector, where all these 3 planes intersect, that's the 3, 0, 1 vector. This is what my solution told me, 3, 0, 3, 3, 1, 0 vector, 3, 1, 0 vector here, right? When can I not have the situation where the planes are so nicely arranged in the 3-dimensional space that they intersect at one point exactly? You know, you have no parallel planes, in which case I would have
a free variable.
But what is a free variable?
It's when you have like it's when you have like a matrix where there's a column where there's more than one value and it can't be reduced any further.
That is correct, but how many people understood this? Okay, if there's anyone who didn't understand this, we'll talk about this. But if everyone understood, then that would be great. Then we'll move on actually to the next subject. If what was just said is clear to everyone. Is that the case? I doubt it. There must be someone who needs clarification. Am I correct?
When you say free, does that a free variable? Does that mean that it's like you can't get it to a 1? Is that what you mean by that?
Okay, so for the record, let's put it down. So I didn't say free at all, right? That's one of you said that. I will say free in a minute. That's because I will explain what the free and pivot variables are. But what was said, I just want to mention that what was said was absolutely correct. So now we'd like to actually define what free variables are. Okay, so let's just talk about that because we need to. Now, the rest of these slides just outline what I've just written by hand. So I'll post these slides so you'll see the solutions. So what we did, notice that the operations that are carried out here are slightly different from the way we mentioned, but at the end of the day, we arrived at this matrix that allowed us to write down the solution by back substituting. But we haven't completed the Gaussian process. So we're not done yet. The Gaussian element, so these guys, okay, so one of you mentioned a free variable. This one doesn't have any free variables. That's why I didn't say anything. The next example will have free variables. These variables with leading ones, in this case, x1, x2, okay, these are the variables below which I have zeros. The last one here qualifies also. These are called pivot variables or the leading variables. If I had a 3 by 5 matrix that has 3 equations and 5 unknowns, I would have ended up with some variables that are not pivots. Those variables that are not pivots are called free variables. Okay, so now, of course, we need to see an example, but that's a good enough definition for what a free variable is, although it provides zero insight if you've never seen an example before. Okay, I mean, I guess if you're checking off some answers to the quiz, I mean, that just Memorizing that definition would do, but it would do you no good in the long run, right? So what exactly is a free variable? Anyway, let me first continue with the Gaussian process, also called Gauss-Jordan elimination. So again, in a classical sense, Gauss stops here. But Jordan says, let's continue. Let's actually make these guys on top of these pivots, zeros. And if I do that, then my matrix would be something like, I don't have it, something like this, with a bunch of ones on the diagonals and zeros above. That's my ultimate goal. And when I come down to this position where my matrix A has been reduced to some other A prime matrix, which is a diagonal, this is called an identity matrix, then I can just read off the solution from the right-hand side. Whatever the right-hand side ends up being, that's the solution X. So in this case, correct sequence of operations were carried out, and I ended up with this right-hand side. Well, this right-hand side, because this is an identity matrix, happens to be the correct solution. This is, by the way, the exact same solution that we ended up with when we did the back substitution. Okay, so again, well, how do you get the matrix in this form? Again, having just pivots on the diagonal. It's a square matrix, and I can have, maybe not, but in some cases, you can get to have pivots, the leading variables, at every entry in the diagonal. You have n by n matrix and you have n pivots. That's the great case where you have a unique solution to the system of linear equations. That's when the unique solution, and only then, the unique solution exists. Anyway, the manipulations are very, very simple. We ended up here. So how do I make a 0 here? Well, I can subtract 3 times this row, 3 times row 3 from row 2, and I end up with this one. I have just made a 0 there. Okay. Okay. Now, how do I make a 0 here? Well, I can subtract row 3 from row 1. That will put me make a 0 here. And of course, I have to be doing this to the right-hand side, right? So I'm subtracting, for example, when I say row 1 minus row 3, from 4, I'm subtracting 1 times 0, which leaves me with 4 still. But these didn't change just because this entry was 0. But anyway, you carry out the same operations. Now, final step, how do I make a 0 here? Well, I subtract row 2 from row 1, and I end up with a 0 there. So now what happened is that I have a diagonal matrix. What does this matrix say? This says x1 equals 3. This says that x2 equals 1. This one says that x3 equals 0. That's the solution. This is my x, 3, 1, 0. Exactly what I wanted to do. This is what your computer software does. Now, let's see other examples. This was a particularly nice example where I had a unique solution in a 3 by 3 case. You normally don't have, well, first of all, you may not have a square matrix. It may be a 55 by 77 matrix in some application. Or it may be a 100 by 3 matrix, like in statistical applications. You have a bunch of observations and only a few, or data science observations. So you have a bunch of a tall matrix, many observations and some, like 100 variables or something, if you're ranking movies or whatever. So these matrices in applications are not square. Now, let's see what this Gaussian elimination does for us. Okay, so let me actually, before I talk about elementary matrices, we do need to talk about them. Let's stick with this example. Let me go to the next set of slides where we'll work with the same example that I've just gone through. And let me define what an echelon form is. That upper triangular form that we got to in the first example was an example of an echelon form. Echelon simply means staircase form. So for example, this matrix is in a staircase. Well, let's actually call that a staircase form, although the more accepted term is the echelon form. This staircase form means the following. I have on the steps, on the very front of the steps, the leftmost positions at the steps, I have the pivots. These guys are the pivots that are sitting on the steps. This is the first example where actually when I reduced this matrix, presumably this was originally a matrix that didn't have zeros in these positions, but I carried out those row operations in this matrix and I ended up with this staircase form. The red circled ones are the pivots. The ones that are not circled, the ones that are not pivots, are going to be, this guy is going to be a free variable. We'll call this a free variable. The reason for why this terminology makes sense will become apparent as we do the next example. Okay, so here's a better picture of what an echelon form or staircase form looks like. These are my pivots. These guys, the squares are pivots, and this guy, for example, here in this 3x5 case, that's a free variable here. That's a free variable. Okay, this is called the row echelon form of the matrix. We normally denote it by U, the analogy for the upper triangular. This is the upper entries. The upper entries in this matrix are non-zero. Okay, called the row echelon form. Now, there is the notion of a reduced row echelon form, where for the pivot, for the free variables, the coefficients by the free variables are made. Oh, I'm sorry. What is it that I'm talking about? Where the coefficients of the variables above the pivots, these guys are made 0, right? Then I will say that my matrix is in what's called the reduced row echelon form. So let's do that example to begin with. Let's take this matrix. Now here's what I'm solving now. Let's start with what's called a homogeneous system of linear equations. You've done the reading in the first 2 chapters. You've read at least the first draft, first reading. You've gone through the first reading already, right? So you don't expect to do it in one sitting, I'm hoping. So you've started reading the first 2 chapters. You've done the first set. Now you know that you're going to return and fill in all these gaps that may not have been understood during the first reason. You'll be reading. You'll be returning to those during your second reading and maybe wrapping it up during your third or fourth reading, right? That's the way it goes. What's a homogeneous system of linear equations based on your reading? Okay, so we're doing the reading before coming to class, right? So AX equals 0 is a homogeneous system of linear equations. You have a matrix times X equals 0. What is it that I'm asking geometrically? I'm applying this matrix. I'm looking for those vectors X that are collapsed into a singularity of a 0 vector. That's what this equation tells me. This system of equations tells me. So please watch 3 Blue, 1 Brown's videos on that. Okay, that's also an assignment. Okay, so we'll clarify what I've just said as we go along. So presumably I have this is my matrix A, and I'm solving the system of equations, AX equals 0, homogeneous system of equations. When I have a homogeneous system of equations, I do not see a particular need of writing down the right-hand side of zeros here, as we did in previously, and carrying those zeros over as I do the row reductions of the Gaussian elimination, because those zeros will stay zeros all the time. So why waste the proverbial ink in writing down the zeros all the time on paper? So we leave that aside and we manipulate just the matrix A. So what happens with A? You take A, you do the row reduction. So here's the first. Subtract 2 times row 1 from row 2 to get a 0 here. So we did get a 0 there. Subtract 3 times row 1 from row 3. So we get a 0 here. Now notice what happened. What happened is that this row became exactly the same as that row. What does that tell me? Well, first of all, the next step of Gauss-Jordan elimination will place the zeros in this position. Right? If you carry out the next step, which is subtract row 2 from row 3 here, you'll end up with a bunch of zeros in the third row. So apparently one of these rows was redundant. Okay, now let me ask you this. Consider these row vectors for a second. This same is true for column vectors, and maybe that's easier to see. Maybe that's not so easy to see, but it's very easy to see it with the column vectors. Consider those outline vectors here. One is blue, and the other 2 are outlined in black. If I add the 2 black vectors, row vectors, to one another, do I not get the same vector here? Right? If I add the black ones, the first 2 rows, row 1 plus row 2 is exactly row 3. What does this tell me? Geometrically, this tells me that the third equation, the third hyperplane, conveys no additional information when it comes to finding the set of solutions that the set of solutions for all 3 equations. The third equation, third hyperplane, gives me no additional information. No additional constraint is imposed on the 4 variables, x1, x2, x3, x4 here. It conveys no new information when it comes to looking for solutions. And that shows up in this reduced row echelon form, when I get a bunch of zeros, there is no information to extract from this equation. It says 0 times x1 plus 0 times x2, blah, 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 0 times everything equals 0. What is it? What constraint is imposed on x's? Nothing. X's can be anything, right? 0 times x equals 0. Is there any constraint in x? No. X can be anything. It's only when I have like 3 times x equals 6 that I can say that I can say x can't be anything. It must be a 2. There's no other way. If I have an equation like this, then x can be anything. Same thing here. When the third row shows up to be 0, apparently one of those equations was redundant. That's the point. Okay. Now, let's see now what are the solutions to. Okay, so these guys, first of all, before we get to solutions, now these guys again are, what are these guys called? I forgot. What are these guys called?
Pivot variables.
Pivots or leading variables. And what are those guys called?
Free variables.
Yeah, those guys are called x3 and x4 are going to be free variables, and x1 and x2 are going to be pivot variables. This means that I get to select x1 and x3 and x4 freely, and then once I do select them freely, x1 and x2 will be uniquely determined. So let me return to this example and do another example first where I have a free variable, just one free variable. And here we have 2 free variables. So it's an interesting example. So let's mark this. We want to come back here, come back. Although we could, stick with this, but let me do a slightly simpler example here. We have it somewhere. Okay, so we'll come back to this. Okay, let's take this one. Consider this example. In this example, I have 2 equations. I have more variables than I have constraints on the variables. So I have 4 variables, but I'm constraining them with just 2 equations. So I have some degree of freedom apparently. So maybe it's intuitive, maybe it's not. But you tell me if this is intuitive, because I'm constraining 4 variables just by two equations, just imposing those 2 constraints. Then I will have some degree of freedom in choosing those variables somehow. I'm not completely constraining those variables. If I had more constraints, if I added more equations to this, then I would be imposing more stringent constraints on how those 4 variables can be related to one another. Okay, now here, let's just go ahead and carry out let's just, here's, you know what? Let's do this. Let's solve this system of equations first by solving the homogeneous system of equations. AX equals 0. So just to be clear, let's write it down one time. We don't always have to write this down, but my system of equations was this. Let me copy it. Okay, so let me just copy that. And this is my original system of equations. I'm going to make these guys zeros for now. So what I'm saying, and I'll return, and I'll undo making these zeros in a moment. So let's solve the homogeneous version first. So this first equation tells me that I'm solving x1 plus x2 plus 3x3 equals 0. And the second tells me that I have 5x1 plus 6x2 plus 7x3 equals 0. This is my original system of equations that was given to me. Then I carried out this Gaussian elimination by subtracting 5 times row 1 from row 2, and I ended up with this system of equations. Okay. Now, the first system says 1, 2, 3, that is x1 plus x2 plus 3x3. That equals 0. That didn't change, same as before. But I've pivoted the second one, the second plane, in the 3-dimensional space, and I ended up with, let me divide this by -4 again. So I ended up with x2 plus 2x3, and let's stick with zeros for now. Now I want to know, what is the solution to this? So question to you, my question to you, solutions to this. So people who have taken linear algebra, or who haven't taken linear algebra. First of all, do I have any solutions? Do I have a unique solution? Or do I have more than just one solution? Can somebody help me out? So let's move on a little bit quickly. We have 40 minutes. I want to do a bunch of examples. more examples. Monday, also examples. Okay, and because we want to move away from systems of linear equations. I don't want to convey the impression that linear algebra is all about systems of linear equations. Far from it. But that's like the basic step. So we want to move away from these row manipulations soon. Please help me out. How many solutions would I have?
Wait, is that if there's free variables?
I'm asking about this particular system of equations.
Oh.
And if you say that I have a free variable, you'd be correct. Which one is free?
I think it should be x3 from the looks of it.
Okay, so why do you think, and why are you not certain of it?
Well, I haven't done actual row manipulations. I just imagine in my head -2 times row 2 plus row 1 replaces row 1, and then you get.
Nothing replaces. Well, what replaces row 1? Okay. So okay, what is it that you're imagining again? Please help us out.
Well, I'm just trying to do the manipulation in my head. It's just -2 times row 2 plus row 1 will replace row 1.
So you are making a 0 here. Is that what you're telling me?
Yeah.
Okay. So let's just do that for a second. So x1. So you're carrying this out further. We could have solved it here, but I'll still ask you what is the free variable here. Because okay, but let's do what you've just suggested first, because we'll eventually end up doing that anyway. So let's just do that. But of course, I'll be asking why is it that we're doing this? But for now, let's just do this. So what do I get here? Well, completely, I have a 0. The whole purpose of subtracting twice row 2 from row 1 was to get a 0 here. So we did here. So we have no coefficient by x2, correct? What do I have here? Do I have a minus x3 here?
Yeah.
Okay, and notice how simple it is with the homogeneous one. I don't have to think about the right-hand sides. Those are going to be zeros anyway. So that's it. Now, what's the solution? So I carried out a row operation here too. And we know by now that carrying out the row the so-called elementary row operations, the 3 operations that we discussed, those do not change the set of solutions. So apparently, whatever solutions this one has is whatever solutions this one has. And conversely, right? Whatever solutions this one has, I didn't lose any solutions, right? Whatever solutions this one has, so they have the same set of solutions. So now let's stick with the simpler one, because this gray one here looks much simpler. So what are the solutions? How many solutions does it have?
It should be infinitely many, right?
Okay, so can you describe the set of solutions? Let's write down the set of solutions.
Here, wait. I haven't done this in a few years.
Okay, so let's figure it out. So somebody, let's do it. Let's do it. And somehow, first of all, do other people agree that I have an infinite number of solutions here? Right? Because do you agree? Why? Yeah, because if you go ahead and plug in, I don't know, -7. Let's just pick a number. I don't know, 55. This is like completely out of the blue. x3 equals 55. Let's write down one of those solutions. I don't know why 55, but let's make x3 55. Then if x3 is 55, right, then x2 has no way but to be -110, right? Is there any way for x2 to be anything else if x3 is 55? So notice that I've picked like x3, I've picked x. Which one is the free variable for those of you who remember what I said a few minutes ago in this row? This is the echelon form, right? So which ones are the pivots? Which ones are the free ones? Which one was the pivot?
You said x3 was the free one?
Yes, x3 was the free one. Notice that I freely chose some value for x3. I said 55. Why 55? Because I pulled it out of the hat. And the rabbit is running around right there too. I'll pull out another one in a minute. But these guys are the pivots. Now, x2, this is the pivot. These two are the pivots. x2, the coefficients by x2. So x2 is the pivot variable. x3 is the free variable. Because x3 is free, I pulled out a value out of the hat. It happened to be 55. Now, x2 has no way but to be -110. And if x2 is -110, then x1 has no way but to be 110. Just back substituting it. But that's just one solution. I could have pulled out of the hat something else. Like, for example, a simpler value. I could have said x3 is 1. Then x2 is -2. And x1 is 2. That's my solution. So apparently the x vector that I was looking for when I was solving this system of equations right? This system of equations, this one. Now solving this. So x that solves this system is 2 minus 2, 1. That's one of the solutions. But not only is that the solution, any multiple of, so this is what does this x give me? It's a vector in 3 dimensions, right? If I wanted to plot this guy in the 3-dimensional space, so here's my, let's say this is my x1 here, this is my x2 here, this is my x3 here. What happens if I plot this guy? Where is this guy? x1 is 2 right here, x2 is minus 1 right there, x3 is right there, 2. So apparently it's some vector that's jutting out like this. Okay, so maybe not Rembrandt here, but it's a drawing of a vector in the 3-dimensional space. Okay, that's the solution. Apparently this point here is the solution to this system of equations. Okay, so that's good. But not only is that point the solution, but any point like this point is also a solution. Where did this point? This point is 55 times stretched this black vector. Well, it's up here somewhere. So that is a solution too. How about minus 1 times this vector? That's a solution too, right? This vector is a solution too. Just what does it mean to multiply this black vector by minus 1? Is to get the red vector, which is in magnitude the same as the black vector, pointing in the opposite direction. The red one is. In fact, every vector on this line, every vector in this line is a solution. Any point on that line, that is a solution to the original system of equations. I have an infinitely many solutions. So these two guys were planes in the 3-dimensional space if you want to draw them. I won't venture to try to draw them in the 3-dimensional space. You can see what my handwriting looks like. But those two planes intersected along this line. These are two hyperplanes. You can imagine like the 2 sheets of paper meeting at an angle, intersecting at this exact line. And that's what Gaussian elimination gave me as a solution. How did I find the solution? Well, I picked the free variable to be something. The purpose of picking a free variable is to pick one point along that line of an infinite set of solutions. And once I've picked one point, then I write down the solution as my all solutions. C times X. Okay, these are all solutions. If somebody asks you to write it down, you write this down, where C is any number, where C is any real number. Now, is this clear? Now let me tell you how the textbook is asking you to write this down, so that you write it down in the quiz the way they're asking you to write it down, so that there's no confusion. Can I erase this piece on the left-hand side, because I want to show you one trick, which if you learn, you'll immediately write down all the solutions to these systems of linear equations that involve free variables that have non-unique solutions. Can I erase? Okay, so please tell me, is this clear what we've just discussed so far? Those of you who are present and are not logged in and are hanging out at the nearest coffee shop right now, if you're present, did this make sense?
Yes.
Okay, good. All right, so now let me please erase this here and show you just one way of writing this down. So, okay, so here's one of our solutions.
I have one quick question.
Yeah, please.
So that exists. So for example, for this matrix, you see how it's 2 by 3, and like the ones we were looking at before were 3 by 3, not including the column on the end, which is the answers, right? Would this same like a free variable thing be the case for all of these ones that aren't like perfect squares? Do you get what I mean?
Yeah. So okay. So you have 2 non-square cases. The non-square case where you have more variables, then you have the constraints. That is the case here. This is like a 3 by 2 matrix, 2 by 3 matrix. So you have 3 variables and 2 equations, 2 constraints only. So here you will end up having free variables for sure.
Okay.
Right? In the case where you have fewer variables but too many constraints, can I ask you what will happen? Like if you geometrically, can you, or should we leave this up in the air?
I think that. I don't know, because I'm thinking about it from the perspective you gave before.
Yeah.
When you first explained these, how you were bringing up how it was like a, like the fats and the carbohydrates example. I'm kind of just thinking of like every example is like just different examples of that happening.
Yeah.
That's kind of what I'm picturing, but I'm not sure what that would look like geometrically. No.
Yeah. So notice what's happening. You have way more constraints on just 2 variables, right? So your matrix is a tall matrix. So this one is a flat matrix. Okay, it's wider than it is taller. In the case where you have more constraints and more equations and few variables, your matrix is tall. It's standing up. Now, because I have more constraints on those, just on the degree of the freedom to which I can vary those two variables, on those I have more constraints. Therefore, I'm less likely to find solutions. Is that intuitive? I mean, we'll make this precise, these notions precise. But is it intuitive that I'm less likely to find solutions unless I get super, super lucky and a bunch of these equations are multiples of one another? That is, I have a bunch of redundant constraints. So one guy says x1 plus x2 is 5, and the other says 2 times x1 plus 2 times x2 is 10, giving me no new additional information on the kind of constraint that is imposed on x1 and x2. If a bunch of those, unless a bunch of those equations are redundant, I really will end up having no solution. So that's the case where you're more likely to have no solutions. Here, you're more likely to have an infinite set of solutions. In the case where you have a square matrix, like the first example that we did, that we ended up with a unique solution, right? That was a nice case. In fact, if you generate a random n by n matrix, you'll end up with a unique solution, right? But it may so happen that you have dependent rows there as well, like repeating rows or rows that are multiples of one another, like in this example I've just given. So that there you can also end up with infinite solutions. That would be the case where the planes coincide, or two planes intersect at a line and the third comes in at the exact same line, right? Unlikely case if you randomly generate those coefficients in a matrix, but it could happen. Right? It could happen in the real world if the data is collected from two different sources and both of these sources collected the same data and recorded it in exactly the same way, then the constraints that you're imposed on the real world variables could end up being the same. You may have repeating equations, right, in the real world too. But let's leave the real world aside. We're really not concerned about the real world right now. Just deal with the problems at this level of abstraction. So, but that was an excellent question, because I will be asking those questions in a minute. So, but where were we? So we have this system of equations here. Now let me tell you how textbooks will normally write this down. Now we imagined this already geometrically. It was this line, everything on that line. So here's the trick that people use. You get down to this. Let me actually copy this. You get down to this, actually here. And to this, what I'd like to do is you add one equation, like artificially. You say, okay, x3 is free, right? So you say x3 is 3. x3 is 3. I'm sorry, not 3. Why would it be 3? x3 is x3. So you rewrite this system of equations as follows. Okay, so let me move away the solution that we know that to be the solution. Let's put this out of the way. So that's the way to write down all solutions to this system of equations. In a minute, we're going to view x3 as a parameter itself, that c that I wrote down, the multiple, to get the entire line out of that representative vector on the line that I just drew 2 seconds ago. What we do is this, and people who have taken linear algebra before, please watch me and tell me if that's the way you did it in your class. I suspect that's the way you did it, but maybe wrong. You wrote this down something like that. Is x3, then x2, I'm rewriting the first two equations for now. x2, you said is going to be the minus 2x3. That's the free variable. Free variables, right-hand side. x3 pivots on the left-hand side. This is what software package does too. It equals just x3, right? Do people see this? Oh, okay, hold on. Did I make a mistake? Oh, did I make a mistake when I subtracted twice row 2 from this one? No, that seems to be correct. Oh, yeah. This seems to be x1 is x3, x2 is minus 2x3, x3 is x3. Okay, so x1, so my x, which is x1, x2, x3, we write down the solution to be, why did I get something else? Did I make a mistake? 1 minus 2, 1 times x3. So notice what I'm doing. I'm taking this vector here, multiplying it by x3. Did I make a mistake? x3 is something, x2 is minus 2 that. This should be correct. Did I write down? Did I make a mistake here? Should be 1, right? All right, so people who are watching me, what happened here? This should be 1, right? This should be 1, right? -2. So this is the set of solutions to the homogeneous system. Let's just check it. Make sure I'm not lying to you here. I have a feeling I made a mistake here somewhere when I copied something. Yeah, this is correct. Should have been 1 there. So I don't know why I had a 2 up there. Anyway, this is the correct solution, right? This is the correct solution. Let's check it one more time. Let's go back to the very original, like the original system. What will this solution tell me in terms of my column picture? In terms of my column picture, what will this solution tell me? Here, let's make space here. What does my solution tell me? That, okay, I'm going back to the column picture. 1, 5, 1, 5 times x1, okay, plus 2, 6 times x2, plus 3, 7 times x3. Those sum up to 0, right? So I'm solving ax equals 0. Ax equals 0. So this system of equations, for now, we're leaving this right-hand side vector, making this to be 0. Now, is it true? Does this solution work? The one that the Gaussian elimination gave us? Is it true that if I take 1 of vector 1, 5, add to it -2 times the second column vector 2, 6, and add to it 1 times the vector 3, 7, will I get a 0? That is the sum of the first and third column vectors, is it the same as the middle vector? This guy. Is it the case? Twice that vector. All right, so we multiply this vector by 2. Do people see that that's exactly what it is? It just works out arithmetically. Do people see this? Because that's the connection we want to see. The row manipulation gives me the solution from the column view perspective. That should be like a new insight. I don't know. The people who have taken linear algebra, was that something that you automatically thought about when you were solving the systems of linear equations? If not, then this is the way you'll think about it now in this run of the course.
What's your question?
Do you see that this works? What does this tell me? What does the solution tell me from the column perspective that we discussed last time?
I remember doing something like this.
Do people see this, that this works out? So we're talking about the linear combinations of the column vectors of A. There's a particular linear combination of the columns. Okay, I can stretch this vector once. This vector, I can add these 2 vectors. If I add those 2 vectors up, I'll get exactly twice the middle vector. That's the point. There's some linear combination of the column vector. The point is that here's the main point. When I get a non-zero solution to the system of linear equations, that tells me, to the homogeneous system of linear equations, that tells me that the columns of that original matrix were linearly dependent. The degree to which the columns of a matrix are linearly dependent, or independent for that matter, is called the rank of A. The rank of matrix A is the number of its linearly independent columns, which, it's not obvious, but that's one of the fundamental theorems of linear algebra. The number of linearly independent columns of A is the same as the number of linearly independent rows of A. That number is called the rank of a matrix. The rank of a matrix is also the number of pivot or leading variables in the Gauss-Jordan form of the matrix. Did that make sense, what I just said? Can somebody repeat the 3 claims I just made, just to help me out, to help everybody else out, those who know. So that, let's just reinforce it. We have a few minutes left. Want to do more examples? We'll do more on Monday. Okay, so people who have taken linear algebra, what's a rank of a matrix, please? Can somebody help us out? Although I said what it was, it may not be clear just once somebody says it. Can somebody help us out? What was the rank of the matrix? Okay, I have
Isn't it the number of non-zero rows? Like
number of non-zero rows in the Gaussian elimination will be the rank of the matrix. That's also true. Yes. what is the number of non-zero rows? How does it relate to the number of pivot variables or free variables in the matrix? In the system of equations. When I do the Gaussian elimination, like for example, we did the Gaussian elimination in one of these guys and we ended up with a 0 row. The number of non-zero rows, how does it relate to the number of pivots? How many pivots do I have?
Well, in this example, there are 2 pivots and 2 free variables.
Okay, so I had an M by N matrix. I came down to, let's say, R equals 2 rows. The number of non-zero rows is exactly the number of pivots, right? Do people see it? The number of pivot variables is the number of non-zero rows, right? Do people see this? For each non-zero row, I must have 1 pivot exactly. Do people see this? So the number of that R is called the rank of the matrix A, of the original matrix, of this matrix. This tells me that there are 2 linearly independent column vectors in A, or alternatively, 2 linearly independent rows of A, right? So for example, same matrix again. Let's take the first column, there's the first column, and let's take the second column, 2, 3, 5. Here's 2, 3, 5. Any other vector, like let's take this one, this guy, is going to be some combination of the first 2, of these first 2, okay? It's just 2 vectors is enough. We'll later call these 2 vectors the basis of a linear space. This vector, this guy, is a linear combination of the same 2 vectors, this guy and this guy, with different other coefficients. With other coefficients, these are the coefficients, I somehow mix them up in different proportions. So I stretch this vector here -1 times, meaning I reversed its direction, stretch this vector twice, I added the resulting vectors up, and I got the third column of A. Same thing here. I did some combination of the vectors to get the 4th column of A. That's how that's it, right? So unfortunately, we're running out of time. We need more examples, but you're reading the first 2 chapters. We'll do more examples on Monday. We'll have, now with a couple of minutes that we have left, first of all, if there are any questions, I'll stay over for a little bit. Let's turn off the video.